Let's take a look at a first example. Say you're the quality control engineer for a manufacturer of electronic subassemblies. And those subassemblies each require a computer chip. You're considering two different suppliers, appropriately named Supplier 1 and Supplier 2. A random sample of 200 chips from Supplier 1 is examined, and 8 are found to be defective. From Supplier 2, we have a random sample of 250 chips, and 13 of those are found to be defective. Okay? So here we're calling our success as a defective. Okay? It's kind of counterintuitive, but that's the notation we've been using all semester. So we have from population 1, Supplier 1, we have a sample of 200 chips. We found the number of successes to be 8. Therefore, P1 hat, the proportion of successes, is 8 over 200, which is 0.04. Okay, so what is our estimator? What is our estimate for the proportion of defective units from Supplier 1 in general? Our estimate is 0.04. From Supplier 2, we collect 250 chips. We see that of those, 13 are defective. Therefore, our point estimate for the proportion of defective units, defective chips from Supplier 2 is 0.052. Okay? And let's say we want to know if Supplier 2 produces a larger proportion of defective chips. We want to know if proportion 2 produces a larger proportion of defective chips. That would mean P1 minus P2 would be negative. Okay? If P2 is larger, then P1 minus P2 would be a negative number. Okay? Larger implies something in the alternative. Okay? P1, we want to know if P1 minus, if we want to know if Supplier 2 produces a larger number of defective chips, that means P1 minus P2 must be less than 0, strictly less than 0. If P2 is larger than P1, P1 minus P2 would be strictly less than 0. Okay, strictly less than 0 does not apply equality. Equality must be in the null. So we have this statement in the null hypothesis. Okay, so now we've just got to calculate a test statistic. That's a z test statistic. That would be P1 hat minus P2 hat. From that, we're going to subtract off P1 minus P2. And we're going to divide that by the standard deviation of the sampling distributions for the differences in the sample proportions. That is P1 hat, 1 minus P1 hat over N1 plus P2 hat times 1 minus P2 hat over N2. Okay? We've got all of these parameters. We just got to plug them in. P1 hat, 0.04. P2 hat, 0.052. The difference that we want to detect, just 0. Down here, we've got 0.04 times 1 minus 0.04 divided by 200 plus 0.052 times 1 minus 0.052 divided by 250. And we're going to take the square root of all of that. Okay? If we work this out, we should get negative 0.608. Okay, so our test statistic, negative 0.608. And we want to draw conclusions, let's say with 95% confidence. So let's find the p-value associated with this test statistic. Okay, so the p-value here would be the area in the lower tail, found from this test statistic, negative 0.608. Okay, this is a z distribution. We want to find this area down here. That is the p-value. Okay, if we go use Excel, or actually we could look this up in the z table. Okay, we could go down to the 0.6 row, the 0.1 column. Okay, and what is that going to give us? If we remember about our table, okay, the table gives us this area, right? between 0 and 0.61. Okay? We want this area. This area corresponds to that right there. Okay? So we're going to have to take what we find in the lookup table, which is 0.2291, and we're going to have to subtract that from 0.5. Okay? So this area right here, the p-value is equal to 0.5 minus 0.2291, which is equal to 0.2709. So this area right up here, 0.2709. Okay, that's our p-value. Okay, that's a very big p-value, bigger than any alpha that we would ever choose. Okay, much bigger than any alpha we'd ever choose. We do not reject the null. P-value greater than alpha, we do not reject the null, and we conclude that that the proportion for population 2 is not greater than the proportion of population 1. The proportion of defectives from supplier 2 is not greater than the proportion of defective chips from population 1. And we draw that, well, we could say with 95% confidence, but our p-value is just very large. It would be larger than any amount of confidence we would ever choose.